or the example that I use is what you call that, bromination. Okay, so basically the general mechanism is the same, except that for the preparation of the electrophile itself. So in the case of bromination, the Br2 is going to be mixed first or with this iron bromide FeBr3, sorry. So the function of this iron bromide is as a catalyst. Okay, if you remember in your chemistry 1 or in general chemistry, the function of a catalyst is to actually lowers the what do you call that, activation energy, or to make the reaction become faster. Okay, but it is not being used in the reaction per se, meaning that if you add one catalyst in the beginning, at the end of the reaction, the catalyst amount will still be the same. Okay, so the function of this iron bromide is to slightly polarize your bromine so that one part of it is positive. So the benzene ring, the electron-rich benzene ring, can attack the positively polarized bromine. Then you have this arin, arinium ion, okay, the arinium ion or the localized cyclohexadiene ion. So this is the resonance structures. So in a general mechanism, this Br will just be E, which is electrophile. Okay, so it can be bromine, it can be chlorine or iodine. Okay, so depending on the type of halogen that you are using. I don't think this is recording. Okay, it's already recording. Okay, this one is the formation of intermediate, already done. Okay, so what you have to remember is the reaction condition and the reagent of each reaction particularly. Okay, so for halogenation, there are 3. So if you want to do a bromination reaction, you must have Br2 and also iron bromide. And if you want to do chlorination, you must have Cl2 with iron chloride as catalyst. But for iodination, so iodine, the catalyst is slightly different, in which that the iodine will be turned into an I plus ion first, okay, using copper chloride. Okay, but fluorine, as you can see here, it is too reactive. Okay, so the reaction is not listed. Okay, here. So only 3 for halogenation that you must know in terms of the reagent and reaction condition. Then we go to the next reaction number 2, which is nitration. So the final product that you will get is actually a nitrobenzene. Okay, you're going to replace one of the hydrogen with NO2. Okay, NO2. So the reagent that you are using is actually nitric acid and sulfuric acid. It's a mixture of nitric acid and sulfuric acid. The function of this sulfuric acid is to produce this nitronium ion. Okay, this nitronium ion. So what does it do is the sulfuric acid, it will remove the what you call that, OH over here. Okay, OH over here, so that the N is only bonded to these 2 oxygen, and the charge is positive because nitrogen actually the allowed bond is 3 with 1 lone pairs. So here, when the lone pairs are being shared to become a bond, the nitrogen will automatically become positive. Okay, so this is nitronium ion. Once you have this, then only the benzene ring can attack the positively charged nitrogen. So a new bond is formed between carbon and nitrogen, and this H2O from here will come and take the hydrogen. Okay, basically the same step as in bromination as well, which is the anion will come and take the hydrogen. Hence, this electron between carbon and hydrogen will be shared back between these two carbon. So the double bond will be retained, and you have your NO2 bonded to this carbon. Okay, so this is the intermediate or the resonance form. Actually, there are another two. Okay, it's the same like this one. Okay, the intermediate, it can be three, but if let's say the question asks you to write like a mechanism, for example, if it doesn't specify for you to draw all of the resonance form, it is sufficient to just draw only one. Okay, unless it is stated in the question to draw all resonance form of the intermediate, then you can draw just one only. Okay, no need to draw all three like this. So this is the product that you will get, nitrobenzene. Okay, this nitrobenzene, if your end product, you want to make it into an amino group, okay, into aniline, what you can do is you can further reduce this nitrobenzene. So reducing reaction by using iron can convert nitro group into an amino group. Okay, but this is the reaction of nitration stop until here. Okay, this is just an addition if you want to convert nitro to amine group, okay, by using this reagent. And then the third one is sulfonation. Okay, sulfonation is when you want to replace or substitute one of the hydrogen with SO3 group. Okay, this one. S O S double bond O S O and also OH. Okay, so the process is called sulfonation, and your reagent that you'll be using is what you call as fuming sulfuric acid, fuming H2SO4, which is a mixture of sulfuric acid and sulfur trioxide SO3. Okay, as you look over here, this is the preparation step of the electrophile. Okay, the sulfur over here is not what you call uh, polarized enough, meaning that we want it to be slightly positive. Okay, but this is not positive enough, so so that this electron in the benzene can attack. So what does it do is the function of this H2SO4 is it will donate one of the hydrogen. Basically, it's not donating. So this oxygen over here will donate one of the electron so that it can take one of the hydrogen from this H2SO4. So now this oxygen is already bonded to this hydrogen. This sulfur will be permanently positively charged. So bila dia dah positively charged, this electron-rich benzene can easily attack this sulfur, which is already positive. This is your nucleophile, this is your electrophile. Okay, hence you will get your intermediate as well, this rhenium ion, same step. The anion, which is this one, will come and take back the hydrogen. So it will turn into H2SO4 again, like this one. And the structure of SO3H will be retained. Okay, and your double bond is back over here. So this is one of the what you call useful starting material, okay, to synthesize sulfa drug. So what is sulfa drug? Sulfa drug antibiotics. So all these antibiotic that contain sulfur. Okay, for example, like this one, in which you have over here you have NH2, which is you can obtain from this reaction, nitration. Okay, once you have your nitro group, you can turn it into amino, and then you can do another reaction of sulfonation to obtain this sulfonic acid, and then the OH you can replace with another NH2, another nitration reaction. Okay. Okay, the last two, which is the the Friedel-Crafts alkylation reaction. So this is reaction number 4. Okay, as the name goes, alkylation. This is where you want to add alkyl group to the benzene ring. Okay, sorry, not add. You want to substitute. Okay, you want to substitute one of the hydrogen with an alkyl group. For example, over here we have this benzene. It is added with this CH32 alkyl. Okay, so the starting material that you need is actually an alkyl halide. So this is alkyl halide. Okay, what you have learned in I think last semester. Last semester you encountered a lot of alkyl halide. Okay, in a few of the topics. So this is alkyl halide, and the catalyst that you will be using is aluminium chloride, AlCl3. So what is the function of this AlCl3? Is to turn this alkyl halide, okay, into a carbocation. Okay, once it becomes a carbocation like this, then the benzene are free to attack the positively charged carbon. So the carbon has already bonded to this carbon in the benzene ring. Then the anion, which is this AlCl4 minus complex, will come and take back the hydrogen. So you have your product, which is a methyl or alkyl substituted benzene plus HCl, and also your original catalyst. Okay, so aluminium chloride, which is this one, promotes the formation of the carbocation, which is this. So alkylation can also proceed with reagents that can form carbocation. So it doesn't have to be necessarily alkyl halide. Okay, you may use other reagent as well, but you have to remember the reaction condition would be different as well. So you can use, for example, alkene, okay, alkene, or in fact you can use alcohol. So if your reagent is alkene, the reaction condition will be 0 degrees Celsius. Okay, 0 degrees Celsius meaning very low temperature with hydrogen fluoride as a catalyst as well, HF. Okay, then you will get the substituted substituted benzene. Okay, the alkyl substituted benzene. So this one is the same. So the alkene can be in a open chain like this, open chain, or in a cyclic form. So if you use alcohol group, okay, like this one, then the reaction condition will be heated. So it need to be heat approximately at 60 degrees Celsius with the use of boron trifluoride as your catalyst. Okay, so remember there are 3 different conditions for Friedel-Crafts alkylation. So if you're using alkyl halide, then you need aluminium chloride for your catalyst. So for alkene, it will be 0 degrees Celsius and also hydrogen chloride. And for alcohol, 60 degrees Celsius with the addition of boron trifluoride as well. Then we look into, before we go to the last reaction, which is the Friedel-Crafts acylation. Actually, the Friedel-Crafts alkylation has a few, what do you call that, limitation or disadvantages. Okay, so the first disadvantages is that aryl halide and vinylic halides actually cannot react. So it cannot be used in the reaction of Friedel-Crafts alkylation. Why? Because their carbocation are too hard to form. First, so what is aryl halide? So this one, and this is a vinylic halide, vinyl. Vinyl involve CH2 double bond CH, this one CHCl. Okay, so these two are very hard to form carbocation. For example, this one, it contains benzene ring. So benzene ring doesn't easily form carbocation because it is very electron rich. Same as well for this vinylic halide. This is a double bond. You see double bond C, so it doesn't normally form carbocation. So your alkyl halide must not be aryl or vinylic halide. So you can use other types of alkyl halide structures except these two, okay, because they are not reactive. Then poor yield will be obtained if the rings, okay, the rings is actually your starting material, which is the benzene. If the benzene already has other substituents, which is amino group or other strongly electron withdrawing group, EWG. So what is EWG? All of this. Okay, you have nitro, you have cyano. This is substituted amine. This is your sulfonic acid, SO3H, aldehyde. This one is ether, carboxylic acid, ester, and so on. Okay, so the reaction, it will give very, very poor yield, and most of the time, it is considered to have no reaction at all because the product obtained is sometimes very, very small. Okay, so 1 and 2 disadvantages. Disadvantages number 3 or elimination number 3 is you're gonna get polyalkylation. Okay, what is polyalkylation or multiple alkylation? Is that first, let's say you have this benzene and you want to add this third butyl to this benzene ring. So once you have this, okay, once you have this product, what actually happen is it will undergo another Friedel-Crafts alkylation. So it doesn't stop with this product, it undergo another type of alkylation. So in a way, this starting material will be substituted again at this position. So you're gonna get two products. Actually, you just want this as your major, but now you're gonna get the byproduct as major product. So this is minor. So this is another disadvantages. And the last one is there will be carbocation rearrangement happen during alkylation. Okay, it is similar to those occurring during electrophilic addition to alkene, and it can either involve hydride shift or alkyl shift. So major product form will be by more stable carbocation. So where does the carbocation comes from? It actually comes from this. So one, it forms this carbocation. So sometimes this carbocation will try to rearrange themselves to be the most stable. Let's say this carbocation away, it is at the first carbon or primary, which is the least stable. So it prefers to be in the middle. So this one is secondary, which is more stable than primary carbocation. Let's look at the example. For example, you have this benzene, and it is reacted with 1, 2, 3, 4 chlorobutane. Okay, But as you look over here, there are two products obtained. One, you have this sec-butabenzene or secondary butabenzene, and you have butabenzene. So if you look at this, what happened is, if this chlorine is already being removed, being taken by this AlCl3, actually this pink carbon will be the carbocation ion. So if the first carbon is the carbocation ion, then you're going to end up with this butabenzene, okay, straight away. But what happened is hydride shift happened, like this one, so that the second carbon, this one, will be positively charged. So once the second carbon is positively charged, it will be bonded here instead of at the first one like this. And since this is more stable compared to this one, then you're going to have this as your major product instead of the primary carbocation ion, this one. Okay. And then another example is alkyl shift. Okay, like this one. Okay, you have this CH3. Okay, there are three CH3 group, methyl group bonded to this carbon over here, and then it's bonded to CH2Cl. An alkyl shift happen so that the carbocation ion, instead of primary, it became a tertiary carbocation ion, which is far the most stable one. Okay, the most stable. So you're gonna end up with not your intended product. So let's say if you want this product, you're gonna end up with this one as the major. So that is one of the limitation. So all of that can be overcome by another type of reaction. So this is the last one, which is the Friedel-Crafts acylation reaction. So instead of using alkylation method, you can use this acylation method. The product that you're gonna get is the same with regards that you can obtain all of the alkylation product. It's just that the starting material that you are using will be slightly different. So reaction of an acid chloride. What is an acid chloride? The general formula will be RC double bond OCl. So this is R, this is R, C double bond OCl. This is actually a derivative from carboxylic acid, okay, which we will cover in chapter 6. Okay, and an aromatic ring in the presence of AlCl3, aluminium chloride. So it still needs aluminium chloride as the catalyst. Okay, it will introduce an acyl group. What is acyl group? It is C double bond OR. So this is C double bond OR. So what you see over here is that the CH3 is being removed. The bond is straight away between this carbon and this carbon. So it avoids many of the problems of acylation. So the advantages, so the good of using acylation is it only substitute once. Okay, so that means there is no polyalkylation or multiple alkylation. Okay, because the acyl group, which is this one, is deactivating. So what does it mean by deactivating is it deactivates this ring. Okay, the ring of the benzene ring become less active, and no rearrangement of carbocation ion like this one. There's no rearrangement happening because you have resonance stabilized cation. So where does the resonance comes from? From this double bond. So there is no rearrangement of the carbocation ion. So what happened in the Friedel-Crafts acylation? Similar to alkylation. So what does it need is this acyl cation. So the first step, the step of the function of this aluminum chloride or the catalyst here is to take this chlorine over here and convert it into this acyl cation. Okay, it will remove this chlorine. So once it removes, this carbon will become positively charged. This carbon will become positively charged. In alkylation, this is where the rearrangement or the carbocation rearrangement happen. But now you have this double bond over here. So instead of rearrangement, it can just form another resonance structure so that it is more stable. So when you have this acyl cation, like this one, the benzene can attack the C plus. The C plus, it form the usual intermediate arenium ion. Then the AlCl4 will take back the hydrogen. So you're going to end up with HCl and aluminium chloride again and your product. So here the product is not an alkyl group. So what you can do is you can reduce it using hydrogen gas with the presence of platinum or palladium metal. Okay, so you can reduce this carbonyl group, this aldehyde or this ketone to become alkyl group. So you have to do for like two-step reaction lah. First you have to do this acylation, then you need to do another reduction reaction, or this one is actually hydrogenation. Okay, but you're gonna get only one product that you want. Okay, there's one intended product. Okay, unlike in alkylation, you're gonna end up with byproduct as well, which end up is the major one. Okay, so summary for all of the reaction, there are 5. So please remember the reagents that you are using depending on the reagents. The reagents and the reaction condition. Okay, so in halogenation, for bromination, you need FeBr3. For chlorination, FeCl3, and then iodination, you need copper chloride, CuCl2. Then in nitration, you need a mixture of nitric acid and sulfuric acid so that it can form nitranium ion. And sulfonation, number 3, you are using fuming sulfuric acid. And for Friedel-Crafts alkylation, there are 3. If your starting material is alkyl halide, you are going to use the same like this one, which is aluminium chloride. If your starting material is alkene, then it will be at 0 degrees Celsius with addition of hydrogen chloride. If you are using alcohol, it will be at 60 degrees and the presence of boron trifluoride. And the last one is this acylation. Okay, your starting material must be an acid chloride, which is this one, and also the addition of aluminium chloride as a catalyst. So to the next part, which is the substituents effect in aromatic ring. So what does it mean is, if all of these example that you see just now, the reaction is just a benzene with no substituents. Okay, just a normal benzene. But what happens if the benzene ring already has another substituents, or maybe more than one substituents to the structures? So it will affect the rate of the reaction, okay, or the reactivity of the benzene ring itself. So substituents can cause a compound to be more or less reactive than benzene. So where is benzene? This is benzene. Okay, hydrogen. That means all of the carbon is bonded to hydrogen. We consider the reactivity to be S1. If you look here, if you replace one of the hydrogen with nitro group, it will make the reactivity to go very low. This is 6 times 10 to the power of -8. So the reactivity becomes very slow. So this is like 0.00000006. So either what do you call that, 8 or probably 9 0. Okay, so very very slow. The reactivity become very low. If you replace it with halogen, for example chlorine, then the reactivity will become 0.033. This is normal. But if you replace the hydrogen with OH, so this is phenol, OH, the reactivity become 1,000 times increase. So it will increase by 1,000 times. Okay, so these substituents have different effect. This is in regards with relative rate of nitration. Let's say you have these structures and you want to add another NO2 group to the benzene ring. Okay, and substituents also affect the orientation of the reaction. So that means the positional relationship is controlled. So what does it mean is, let's say you already have one substituent at the original structures, you want to add this nitration. So the new nitro group can be at either ortho or para or meta. So these substituents, all of these substituents, it can be either ortho and para directing activators. That means it will direct the new substituents to ortho position or para position. And also we have this ortho para directing deactivators. So deactivators, that means it will go to ortho para, but it also deactivate the rings. It make the rings less reactive. And the last one, we have this meta directing deactivators. So meta, for example, at this one, it will go at this position, meta. And it will also deactivate the ring. Where does this substituent effects comes from? I believe this you have encountered in your what do you call that, basic principle of organic chemistry. It is known as inductive effect and also resonance effect. Resonance we have covered last unit. So in inductive effect, movement of electron, movement can be withdrawal or donation of electron through a sigma bond, meaning single bond. Okay, single bond. Then we have this resonance effect. So it can be movement of electrons through a pi bond. Okay, pi bond. Inductive effect, sigma bond. Resonance effect, pi bond. Okay, due to the overlap of a p orbital on the substituent with the p orbital on the atomic ring. So let's take a look at inductive effect first. So how does these substituents have this inductive effect? So it can be both withdrawal or donation depending on the type of the substituent itself. So for example, it will control this inductive effect. It is controlled by electronegativity. So if you already forget what electronegativity, go back. Okay, go after this, try and Google what is electronegativity. Okay, it is based on the Pauling scale, with fluorine being the highest value of electronegativity with 4.0. So you need to know what is electronegativity first. Okay, and the polarity of bonds in functional group. So that means you have to compare between carbon and whatever atom on the substituent is, which is more electronegativity. So for example over here, halogen, carbonyl, cyano group and also nitro group will withdraw electrons through this sigma bond connected to the ring. So how? For example, here we look at this chlorine and also carbon. So between this chlorine and carbon, chlorine will be more electronegative compared to the carbon. Okay, refer to the Pauling scale. Okay, so between these two, chlorine will be more electronegative. So the electron between these two in the bond will be pulled toward chlorine. Okay, it will pull toward chlorine. So The definition of electronegativity, tendency of an atom or group to attract shared electron towards itself. So it will take or pull the electron in the bond over here towards this side. Same as well for this OH group. O is more electronegative compared to this carbon over here. This one as well, because on this carbon, even though you have carbon, on this carbon you have oxygen. Okay, this one you have nitrogen, and this is nitrogen with 2 oxygen. So all of this is withdrawing electron from the benzene ring. But if you have alkyl group bonded to the benzene ring, it will donate. That means the carbon, because this is carbon, but between these two carbon, the carbon on the benzene ring is more electronegative. So it will pull electron from this alkyl towards itself, so towards the benzene ring. So this is considered inductive electron donation. Then we have resonance effect. So resonance effect also have electron withdrawal and electron donation. So here we have, we look at how does this C double bond O, C triple bond N, and also this nitro group withdraw electrons from the aromatic ring by resonance. Okay, so look for a double or triple bond connected to the ring by a single bond. Connected to the ring by a single bond. That means you have this double or triple bond. It is connected to bond. Then this is the ring. So it forms resonance structures, but it pulls electron. So it pulls electron from the ring. You see the arrow is moving from the ring. Okay, moving from the ring. So this is electron withdrawal. This is electron donation. So this happens to the substituents that does not contain any double or triple bond. For example, halogen, OH group, or hydroxy group, or alkoxyl group, and also amino substituents. Okay, the pi electrons flow from the substituents to the ring. For example, this one, it goes from chlorine into the ring. You see the movement of the arrow. So this is, all of this is considered to be donation. So an explanation of the substituents effect. So if you look here, activating groups will donate electron to the ring, thus stabilizing the carbocation intermediate. So if you see any group or substituents donating electrons into the ring, hence it will make the ring more active. When it becomes more active, then the reactivity of the reaction will be higher. But deactivating groups withdraw electrons. So it will take electron from the rings. Okay, remember the ring is electron rich. But if you give the rings more electron, it will become more active. But if you take away the electron,